So now that we've had one example of Gauss's law, that is deriving Coulomb's law from Gauss's law, let's look at a few more examples of Gauss's law. Here's a problem. An insulating sphere, radius A, has a uniform charge density ρ and a total positive charge Q. Calculate the electric field outside the sphere. Well, we're going to construct a Gaussian surface of arbitrary radius r, where r is greater than the radius of the sphere itself, A, and we're going to apply Gauss's law to that surface. So we're going to have E dot dA on that surface is equal to the charge enclosed over epsilon naught. Well, like before with the Coulomb's law derivation, we're going to find that the E field is emanating radially outward in all directions. Hence, on the Gaussian surface, the E field and the area vector are going to be parallel everywhere on that surface. So E dot dA is going to be equal to E dA cosine 0, which is just going to be E dA. So E dot dA is E dA. Also, since so now it looks like the integral E dA equals charge enclosed over epsilon naught. Since this spherical charge distribution is symmetric everywhere, there's no reason why the E field should be any stronger at one point as opposed to another point. So the E field is constant everywhere on our Gaussian surface, and because it's constant, we can take it out of the integral, because you can always take a constant out of the integral, and we end up with E integral of dA is equal to the charge enclosed over epsilon naught. The integral of dA is simply the area of our Gaussian sphere, which is 4 pi r squared, and the charge enclosed is Q. So we now have E times 4 pi r squared equals Q over epsilon naught. Solving for E, we have E is equal to 1 over 4 pi epsilon naught, big Q over r squared, which is our K electric, big Q over r squared. This E field looks like a point charge if we're at a distance r greater than the radius of the spherical distribution itself. Makes sense. We've seen that result before as we get further away. What happens, though, if we go inside the distribution? Now we're going to have a Gaussian surface of some arbitrary radius r that is less than the radius of the distribution. The main difference here is that we're going to enclose a fractional amount of the total charge available. And that fractional amount is going to be equal to the volume of our new sphere, 4/3 pi r cubed, to the volume of the charge distribution, 4/3 pi a cubed. So our charge enclosed is going to be the ratio of those volumes, 4/3 pi r cubed to 4/3 pi a cubed, times the total charge available, which is big Q. That's what's going to be enclosed in our Gaussian surface. The 4/3 pi cancels out. And we have Q enclosed is equal to r cubed over a cubed times big Q. By symmetry, the E field will be parallel to the area vector everywhere on our Gaussian surface, and it will be constant everywhere on that surface like we had before. And the area of our Gaussian surface will again be 4 pi r squared. So everything on the left-hand side that we had before will apply again as far as our progression in solving that integral. So E times 4 pi r squared is going to equal our charge enclosed over epsilon naught, which is r cubed over a cubed times big Q that we just determined. So if we solve this for E, we're going to get rid of r squared on both sides, and we have E is equal to 1 over 4 pi epsilon naught QR over a cubed, which is KQ over a cubed times r. R is our variable going from 0 to a, and everything else is a constant out front. So we see that our E field is linear as we go from 0 to the radius of the sphere. It's going to increase in a linear fashion with R. Outside the sphere, it acts like a point charge. Inside the sphere is linear with R. If we were to graph this, it would look something like this. We have a linear line going from 0 to some value at the surface. Once we get there, it drops off with R squared as we get further and further away. As the E field, as a function of radius or distance from the center for a spherical uniform distribution of charge. This is the same kind of result we would get for a gravitational field for a mass distribution of charge in a spherical sense. In other words, if you had the Earth as a uniform mass, you went to the center of the Earth, the gravitational field there would be 0. It would increase linearly as you went towards the surface of the Earth. Once you got to the surface, it would drop off as your distance squared, just like this relationship here on this graph. We can note that when R is actually equal to the radius of the sphere, A, then E will be equal to KQ over A squared, which is a continuous point between these two values here. In other words, we don't have any discontinuity in the field. We go up to the radius, it's equal to a value there, and as we proceed from there, it drops off. But at the surface of the sphere, it's equal to the same value. Okay, let's try another example. A thin spherical shell of radius A has a total charge Q distributed uniformly over its surface. Find the electric field at points outside the shell, and then we'll look inside the shell. So we'll construct a Gaussian surface of some radius R outside the shell, and we'll write down Gauss's law, and we'll apply Gauss's law to this new Gaussian surface that we just constructed. Now we'll see, as before, the E field is going to be radially outward, and it's going to be parallel to the area vector everywhere on this surface. So E dot dA will be equal to E dA cosine 0. And the E field will be constant everywhere on the surface. There's no reason why, because if you look at it, it's symmetrical any way you look at it. So there's no reason why the E field would have a greater value anywhere as opposed to anywhere else. It'll be constant on the surface. So everything that we applied to the left-hand side of our Gauss's law will again apply here. Take the E field, the constant, out of the integral. We're integrating over the surface of our Gaussian surface, which is just going to be the area of that sphere, 4 pi r squared. And so we have E times 4 pi r squared is equal to the charge enclosed, which is the charge on the sphere, Q over epsilon naught. E field will equal 1 over 4 pi epsilon naught, big Q over r squared, or K electric, big Q over r squared. It's looking like a point charge if our radius is greater than the radius of the sphere itself, just like what we had before for the distribution of charge. But what happens if we go inside this shell of charge? We'll select a Gaussian surface that goes arbitrarily close to the inner surface, but we can see right away that it's enclosing no charge. In other words, we're inside the shell, and there's no actual charge inside our Gaussian surface. So if we write down Gauss's law, we can immediately say that Q enclosed is actually 0. And as we solve this equation, then, we'll come up eventually with the fact that the E field inside is 0. We've got flux going through, but whatever goes in goes out of our Gaussian surface. There's no flux-producing device inside our Gaussian surface, so the E field must be 0. We have a name for this kind of construction. It's called a Faraday cage. It's a cage which allows charge to build up on its surface, but in essence is shielding you from the external fields so that you have no E field inside due to the external fields. At the University of Minnesota, where I went to undergraduate university, in the basement of the physics building there, they have a big room that has these metal sheets all the way around, or these metal bars all the way around, like a big cage. And if you go into that room, you can conduct an experiment without fear of having interference from electric fields outside. The big room shields you from electric fields outside. At least that's what they told me when I misbehaved and they stuck me and locked me in that room. Okay, just kidding. Here's another problem. Let's find the electric field at a distance r from a uniform positive line charge of infinite length whose charge per unit length is lambda. So we have a charge per unit length. We want to choose a Gaussian surface that has the same symmetry as our charge distribution itself. So we have a line of charge. We're going to choose a cylinder to encompass it. And we'll apply Gauss's law to this Gaussian surface. Now if we look at this from a top view, we'll see that the E field is emanating radially outward, and it will be parallel to the area vector everywhere on the outside of our cylinder, not on the end caps, but on the curved part of our cylinder. On the end caps, there will be no flux going through those because the E field is going outward like this. So we only need to consider the area of the outer surface of our can, of our cylinder, if you will. The E field will be parallel and it will be constant as well because by symmetry we can look at this cylinder at all different angles and it looks the same. So on the left hand side of our Gauss's law we have E parallel to dA, so E dot dA is equal to E dA. E is constant on the surface, so we can take that constant out of our integral, and so we now have E integral dA, and now we just have to find the area for which that E field, that flux, is going through, and that's just the area of this can. So how do I find that area? Well, if I took a tin snips and went and cut this can and then spread out the can, I would find that the area would look something like this. If I have some length L, the other width of the can is going to be 2 pi r, the circumference of that circle, and hence when I spread it out, the area is going to be the area of this rectangle, which is going to be 2 pi r times L. So my area is 2 pi r L. So now the left-hand side of Gauss's law will be, for this situation, E times 2 pi r L, because there's no flux going through the end caps, is equal to the charge enclosed over epsilon naught. What is the charge enclosed? Well, if I have this can, this Gaussian surface around this line of charge, the charge enclosed is that part of the line that's actually in the can. That's going to be the length L times the charge per length for this line of charge. So it's going to be lambda times L. That's the charge that's actually inside my Gaussian cylinder. So my charge enclosed is lambda times L. I can get rid of an L on both sides of this equation. And now I have that the E field is equal to lambda over 2 pi epsilon naught r, which I could write as 1 over 4 pi epsilon naught, 2 lambda over r, which will be our K electric, 2 lambda over r. K, 2, and lambda are all constants, so my E field is dropping off as my distance r. This is the E field outside of a line of charge. Let's look at one more example of Gauss's law. We have an infinite sheet of charge per area, sigma. We're going to put in another Gaussian surface, another can, if you will, but this time the flux is going to be going through the end caps of the can, not on the sides. So we only need to concern ourselves with the cross-sectional area of this Gaussian can, this Gaussian cylinder, and not with the area on the sides. We're going to apply Gauss's law to this, and we'll see immediately that we have flux going through one end cap and flux going through the other end cap. So it's going to be E times A over here and an E times A over here. So E perpendicular to A has no contribution. E parallel to A is going to be E times A, cosine 0. And we're going to have two of them, so it's going to be E times 2A, where A is the cross-section of this can. And that's going to equal the charge enclosed over epsilon naught. Pretty easy. I'll also recognize that the charge enclosed is just that charge in that little disk that is enclosed inside my Gaussian surface. That's equal to the cross-sectional area of the can times the charge per area. That will be the charge that's on that little disk inside the can. So that's going to be sigma times A. So now we have, solving for E is equal to 1 over 2A, sigma times A over epsilon naught. A's cancel out. And we have that the E field is equal to sigma, the surface charge density, over 2 epsilon naught. It's constant. Sigma is a constant. Epsilon naught's a constant. The E field's constant. If I'm near the sheet of charge, I can be anywhere, and the E field will be the same. It's constant. This is the same result we got in Chapter 23, looking at distributions of charge. We were looking at the disk of charge, and we said that if you're relatively close to the disk, it looks infinite to you, and we concluded after our integration of the E field that we got the same result. The E field was equal to a constant, sigma over 2 epsilon naught. So all this we can conclude in one table here. If we have an insulating sphere of radius r, uniform charge density rho, total charge q, that outside this distribution, spherical distribution, acts like a point charge, k big Q over r squared. Inside, it acts linearly from 0 to the surface. And so it's k q over r cubed times our variable r. For a spherical shell, radius r and total charge q, outside acts like a point charge, k q over r squared. Inside, there is no E field. And this would actually be the same as if we had a spherical conductor. Because a spherical conductor, the charge will move as far as it can from the like charge. If we had some net charge on a conductor, it's all like charge, so it'll move as far away as it can from the other like charge, which means it will reside on the surface, like a shell. And so the E field inside will be 0, and outside it will look like a point charge. A line charge of infinite length and charge per unit length of lambda is going to be 2k lambda over r. A non-conducting infinite charge plane having surface charge density, charge per area sigma, is going to be sigma over 2 epsilon naught. It's going to be a constant, where we have flux going in either direction from the charge plane. If we had a conductor, a surface conductor, having a surface charge density sigma, E field on one side, on the interior of the conductor, is going to be 0. On the other side, it's going to act like a plane, sigma over epsilon naught. So on one side, on the outer side, it's going to be sigma over epsilon naught. On the inside, it's going to be 0. And so this is like a sheet of charge, only we don't have the E field going on one of the sides. It's 0 on that side. So that's why it's sigma over epsilon naught instead of sigma over 2 epsilon naught for a conductor. Speaking of conductors, if we had a conductor in electrostatic equilibrium, we will have the following 4 properties. The electric field is 0 everywhere inside the conductor. This is justified because if it were not 0 and we had charges inside the conductor, they would move under the non-zero electric field until they could move no more. And hence, eventually, we would establish electrostatic equilibrium where they are no longer moving. Any excess charge on an isolated conductor will reside entirely on the surface. If I had excess charge, either positive or negative, it's going to move away from the like charge and try to get as far away from like charge as it possibly can. So if I had a conductor, that charge is going to reside on its surface, pushing all the charge as far away from the like charge as possible. The electric field just outside a charged conductor is perpendicular to the surface and has a magnitude sigma over epsilon naught. Everywhere where the surface charge density sigma is a charge per unit area at that point. We just proved that with Gauss's law and the sheet of charge. On an irregular shaped conductor, the charge tends to accumulate at locations where the radius of curvature of the surface is smallest, that is, at sharp points. If I had a conductor and the charge is residing on the surface, let's say it had a sharp point, that charge on the surface would be forced on that geometric location of the sharp point to be closer together at that point. Hence the E field, due to that charge, is going to be strongest, of greatest magnitude, at the pointed part of the conductor. Hence, external charges to that conductor will see that larger E field at the point and be attracted to it. If I had charge in the air, in fact, if I had a charged cloud and there was a streamer coming down from the charged cloud and it saw this pointed conductor, it would see the E field there, and that charge would be attracted to that and would basically discharge the air, or allow it not to build up any more charge to the point where you might have a large discharge called a lightning strike. It would diffuse that and allow you to protect your house. So that's the idea of a lightning rod, is to kind of diffuse the air so that you don't ever set up a complete path for the charge to flow. Ben Franklin is credited with designing the lightning rod, and it was a great design, and it was appreciated as protecting buildings. The French saw this and they said, yeah, lightning rod sounds good, we'll protect buildings, but you know what? And those Americans, they don't know how to make things beautiful. And so they decided to change the design of the lightning rod. They made them more curved so they were more aesthetically pleasing, yet they didn't work. So at least they looked good, but they didn't protect the buildings because they didn't have the sharp points that you needed in order to diffuse the charge. That was the whole idea behind the lightning rod, was to diffuse the charge in the air. Here's the ice pail experiment by Faraday. And if you took a charged ball, put it into a neutrally charged ice pail, it would induce charge to form of the same magnitude but opposite charge on the inner side of the pail. And since the pail is neutrally charged to begin with, that means an outer part of the pail would form a similar magnitude positive charge. If you continue to move that ball down and touch it to the inner surface of the pail, you could diffuse that pail with the same magnitude charge and leave the outer surface of the pail positively charged. Hence, in essence, what you have done is transfer the charge from your ball to the surface of the pail. If you continue to do this, you could keep on adding charge to that surface of that pail and build up charge on that pail. This is basically the idea behind a Van de Graaff generator. It's one big pail, and you bring in charge through a conveyor belt, and you keep on adding that charge to the outer surface of your pail until the point where the E field becomes so large it breaks down the air, and you start getting little lightning strikes going from your Van de Graaff generator. So that's the basic principle of that, using this Faraday pail. That concludes our second lecture in Chapter 24